In the first half of this chapter, we focused on categorical data. And categorical data, we were able to calculate proportions. What proportion of the whole was that category? We are now going to change over to quantitative data. And if you remember, quantitative data was your data that was numerical. We were able to calculate statistics from it, such as the mean or the median. So, like any statistic computed from a random sample, sample means for quantitative data also has a distribution, just like we looked at with proportions. So we're going to look at a couple of pictures. If we simulated tossing a fair die 1,000 times and recording what number appeared each time on the die, we will get something that looks like this graph below. The numbers 1 through 6 and roughly even on all of them. Not perfectly even, but for the most part, even. So, a couple of quick questions. What's the shape of this graph? Maybe you might say flat. More appropriate word would be technically uniform, the same all the way across. What's the mean of this graph? Well, there really isn't a mean that you can calculate because there isn't really anything higher than the rest of them. So there really is no mean. Now we're going to step it up a little bit. We're now going to look at more than just one die. So now we're going to take 2 dice and we're going to roll them and we're going to average the numbers that we see. So here's now the results from 10,000 rolls for 2 dice. Notice this graph is no longer flat. Maybe you might call it triangular, because it does definitely look like a triangle. Maybe you might use the word symmetric. But all of a sudden we start to see a shape. Is there a mean? Is there a number that occurred the most? Well, it's looking to be maybe 3.5 is the average result. Look at 3 dice. Now do you start to see a little bit of curve on this side? Maybe a little bit on this side. It's not quite as triangular. It's a little more curved. It's definitely still looking pretty symmetric. What about that mean? Does it still look like it's kind of here somewhere in the middle? So somewhere around 3.5 is the mean. Now we're going to expand even larger. All of a sudden now we have 2 more options. We have 5 dice and 20 dice. Well, if you look at 5 dice compared to, say, the 3, you should start to see even more curve in the graph. And if you look at 20, all of a sudden it should be a much more definitive peaked curve. Any word that comes to mind when you start to think about this? Hopefully at this point you're starting to say, okay, I see the shape. It's the same shape we've seen before. The shape looks like the normal model. And that is not a coincidence. The more dice we utilized, the more and more it became normal. That leads us to what's called the fundamental theorem of statistics. The sampling distribution of any mean, because when we have quantitative data, we always focus on the mean, becomes more and more normal as the sample size grows. So the bigger the sample size, we changed from 1 dice to 2 to 3 to 5 and then to 20, the larger the sample size got, the more normal the graph looked. All we need for the observations is to be independent and random. Independent, if you remember, meant that the first roll never affected the second roll, or the first thing never affected the second thing. And, of course, random, something we've been using a lot. We don't even care about the shape of the population. The population doesn't matter. All we're focused on is the sample. The fundamental theorem of statistics is also referred to as the central limit theorem. So we're going to take a look at how this central limit theorem works a little bit and some important information about it. So in order to use the central limit theorem, we have some assumptions that we need to make. The first assumption that we would like to make is the independence assumption. In other words, that each sample is independent or doesn't affect the other samples. We also need to make a sample size assumption. That is that the sample size, which same letter we've used before, n, has to be large enough. Well, how can we make those assumptions? We have to check the same exact conditions that we checked before, minus the NP and the NQ. We still need to check the random condition. It should be stated somewhere in the problem, the concept of random. And the 10% condition, if you remember, the sample size n must be no larger than 10% of the population. This was when I talked about simply take the sample size and tack on a 0, and as long as the population is that big, then we're good. So let's look at some important formulas. So the sampling distribution model for a mean, again, the central limit theorem. The important information, a random sample is obviously drawn from any population. Now the population information, okay, this is population info, has mean, if you remember, this guy right here is mu, that's how you say it, it's the Greek letter, with standard deviation, this little guy here, whoops, he is, I started to write, but then it messed up. He is sigma. We learned those way back in chapter 3, I believe, 3 or 4. So that's the info for the population. The sample mean, which we signify with y bar, just happens to be the exact same mean as the population. So that's the nice thing. The population mean and the sample mean are exactly the same. However, the sample standard deviation is not. The sample standard deviation is the standard deviation from the population divided by the square root of n. And if you remember, n is your sample size. So the means stay the same when we go from dealing with a population to dealing with a sample. However, the standard deviation ends up getting smaller because we're changing the size of, obviously, the group we're focusing on. So let's take a look at a very basic application of the central limit theorem. An automatic character recognition device can successfully read about 85% of handwritten credit card applications. To estimate what might happen when this device reads a stack of applications, the company did a simulation using samples of size 20, 50, 75, and 100. For each sample size, they simulated 1,000 samples with success rate of 0.85 and constructed the histogram of the sample proportions that are shown. We are going to explain how these histograms demonstrate that the central limit theorem, what the central limit theorem says about sampling distribution models for sample proportions. So if you notice the very first one, this graph right here, this was for the sample size of 20. If you look at the graph and you think describing what it looks like, to me that looks very skewed. Okay, you see a definitive tail over here on the left. You see your high bars on the right. Sample size, 50. Not quite as obviously skewed because we do have a little bit of a tail on each side, but it's definitely still heavier to the right side. Then we look at sample size of 75. Now you're starting to see kind of low bars on both sides, and you're kind of starting to see a little peak in the middle. And then finally, the sample size of 100. Now you should start to see the bell-shaped kind of curve. you should see that it's looking much more symmetrical on both sides instead of heavy on one side. So this describes exactly what the central limit theorem says. Obviously, as n got larger, and remember n is the sample size, the shape became much more unimodal and symmetric. Or in other words, it became much more normal. So we're going to do some further detail with these four histograms. So the automatic character recognition device that we were just talking about that successfully reads about 85% of handwritten credit card applications. In example 6, we looked at the histograms, and it showed the sample proportions from 1,000 simulated samples of sizes 20, 50, 75, and 100. Here are the more detailed statistics from each simulation. So when the sample size was 20, it lists the mean from that sample and the standard deviation. When the sample size was 50, it shows the mean and the standard deviation. When the sample size was 75, same thing. And when the sample size was 100, same data. So according to the central limit theorem, what should the theoretical mean and standard deviations be for these sample sizes? So the central limit theorem says that the mean for each one of these samples, which we called y bar, should be the same mean as the population. And the population says that it successfully reads 85%, or 0.85. So according to the central limit theorem, that's what the means should be. Well, if you look at the means in our table, I wouldn't say we were too far off. Some of them were a little low, some of them were a little high, but for the most part, they were pretty close to 0.85. We also need to figure out what should the theoretical standard deviations be. Well, we're not going to use the formula that I showed you before. And the main reason for that is the standard deviation formula for means, or for samples, was this: the standard deviation from the population divided by the square root of n. The problem is, on this particular problem, we don't know this guy. We don't know the standard deviation from the population. So we're going to calculate the standard deviation using our methods from the last lesson. And if you remember, from the last lesson, we learned that the standard deviation was always the square root of p times q divided by n. So I'm going to calculate that for each and every one of these. Now the nice thing is, for this problem, p and q is not going to change, because the probability or the proportion of correct applications is 0.85, which means the incorrect proportion is 0.15. So the only thing that's going to change from one sample size to the next is your n. So let's do some quick calculations. So the first one would be 0.85 times 0.15 divided by 20, all under the square root. And if you type that in the calculator and you use two non-zero digits like we talked about, I get 0.080. So that was for the first line. Let's do the second one. Again, the only thing that's changing is we're changing the 20 this time to a 50. If you type that in the calculator, I get 0.051. Then we're going to change this time the 50 to a 75. You type that one in the calculator, I get 0.041. And then finally, we're going to change that 75 to a 100. And I end up with 0.036. So if you look at the standard deviations that we got from the samples compared to what our formula says they should be, 0.080 compared to 0.0803. All we're missing is a decimal place. 0.051 to 0.0509. You're talking about rounding. So these are very, very close. And we have a couple more questions that deals with this table. So you're going to be referencing back to this in just a minute. So how close are the values that we just calculated to the ones in the simulations, in the actual samples? When we compared the means and the standard deviations both, everything was very close. There was no significant differences at all. So let me ask you, when we looked at those 4 histograms, what sample size would you feel comfortable using the normal model to approximate? So if you look back at those pictures, if you remember that first one was very skewed left. Skewed left. The right one, or the second one, the sample size of 50, was also kind of skewed. It definitely was not going towards symmetrical. Now, I would confidently say that we could use it for a sample size of 100. No doubt. That looked very normal looking. But do you think it would work for a sample size of 75? What do you think? Do you think we could use the normal model for 75? You know, that's a decision that maybe is not as easy to make. The nice thing is, our success failure, our NP and NQ rules that we've learned before, we can easily decide right now whether both of them are okay. So let's start with the one we were confident about, the 100. So if we calculate NP and NQ, this would be 100 times 0.85 and 100 times 0.15. Well, that will give me 85 and 15, both of which are greater than 10, so absolutely no issues saying yes to 100. The 75 was the question mark, so let's calculate the same thing. So this time it's 75 times 0.85 and 75 times 0.15. Well, it just so happens that the first one comes out to be 85, which definitely no issues there. I'm sorry, I looked at the wrong number. That one comes out to be 63.75, which is no issue. The other one, which is definitely smaller, is 11.25. Well, the only rule was they had to be bigger than 10. So, technically, we could say on both the histogram for 75 and the histogram for 100 that we feel comfortable using that to calculate data. So now that we've kind of done a little bit of introduction and realized that our sample size need to be bigger, we're going to look at some applications of the normal model. So statistics from Cornell's Northeast Regional Climate Center indicate that Ithaca, New York gets an average of 35.4 inches of rain each year, with a standard deviation of 4.2 inches. First of all, the info that I just gave you, the average of this and the standard deviation of that, that's your population data. That is for Ithaca, New York, all of history. So we assume that that is your normal population data. Nice thing it says here, we can assume that a normal model applies, which means we don't need to check any conditions whatsoever. We can make that assumption because it's told in the problem. So, basic z-score question. During what percentage of the years did Ithaca get more than 40 inches of rain? This is a basic normal model z-score problem. So, obviously, when we calculate z-scores, it's always the x value, which in this case is your 40 inches, minus the mean, which is 35.4, divided by the standard deviation of 4.2. We've done this before, not a big deal. Round to 2 decimals, you get 1.10. If we think about our little picture. 0 is in the middle. 1.10 is over here. Keyword, more than. Shading to the right. So what that means is when we go to our blue sheet and we look up 1.10 on our blue sheet, we have to take 1 minus that answer. And so the blue sheet says 0.8643. So when we subtract from 1, we end up with 0.1357. So this was a straightforward problem. We could have seen this back in chapter 6 when we first learned z-scores. Less than, so that should tell you something about shading. Less than how much rain falls in the driest 20%. So the driest 20% means that the lowest 20%. So when we're talking about a picture, 0 being in the middle, we're talking about this area over here. The problem is, this is a working backwards problem. You don't know the z-score, you don't know the x value, and so we have to do some backwards thinking here. So we know that the probability that this little area right here is 0.20. I'm going to tack on 2 zeros. That's the probability. This is the number, if you're looking at your blue sheet, from the center of the blue sheet. Now, it's been a while since we've worked backwards on z-scores. So pick up your blue sheet, go to the negative side, and start looking in the middle for the closest number you find to 0.2000. When you find it, arrow to the left and arrow up and figure out what z-score that actually represents. Now the z-score I got that is closest to that is negative 0.84. Hopefully you got that z-score. If you didn't, make sure in class you come up to me, make a little note right now in your notes, ask Miss Simon how I got that number. Now that we know our z-score, now we can do our working backwards. So our z-score is negative 0.84. The z-score formula always starts off with x. Well, we don't know x. Minus our mean of 35.4 divided by our standard deviation of 4.2. All right, we're in algebra land. We need x by itself. First thing you should be thinking, multiply by 4.2 on each side. That's going to cancel those. If you use a calculator, you should get negative 3.528 equals x minus 35.4. To finish getting x by itself, you add 35.4 to both sides. So the rain for the driest 20%, once you add those together, is 31.87 inches of rain. So the driest 20% of the years only got 31.87 inches of rain. Now, what we've been doing here is 100% review from Unit 6. We're going to tie in now how this applies to our new stuff. So, a Cornell University student is in Ithaca for only 4 years. Let y bar represent the mean amount of rain for those 4 years. So now we need to describe our sampling model. Well, we know that it's acceptable to use the normal model. But because we now have a sample, our mean, y bar, and our standard deviation for y bar might change. Well, what we learned about the central limit theorem is that the mean for all samples is the exact same as the mean for all of the population. So that doesn't change. That's the 35.4 and it's going to stay. However, we have a formula to calculate standard deviation for samples. And that was the standard deviation for the whole population divided by the square root of n. Well, the original problem, the standard deviation was 4.2. And we are dividing this by the square root of, our sample is a 4-year sample. If you type that in your calculator, exactly how you see it, you should get 2.1. So now that we're focusing on a sample only, the mean stays 35.4, but the standard deviation drops to 2.1. So now we're going to answer another z-score related question. What's the probability that those 4 years average less than 30 inches of rain? So now we can calculate our z-score because our x value we're focused on is 30. The mean is still 35.4, but the standard deviation is now 2.1. So our z-score should change. Our z-score, I end up with negative 2.57. If we think about our drawing, 0 is in the middle, negative 2.57 is over here. Now, it's asking for less than 30 inches. So that means we're shading to the left only, which means no need to subtract. We're just going to look it up on our blue sheet, and we get 0.0051. So that is the probability that in those 4 years, you get an average less than 30 inches of rain. Let's look at another example, tie this into some of the other old stuff we've been doing. You pay $10 and you roll a die. If you roll a 6, you win $50. If not, you get to roll a second time. If you get a 6 the second time, you get back your $10. So you've seen these tables before. Let's just go through some old steps. So what are our outcomes here? Well, best case scenario, you roll the die, bam, you get a 6 on the first roll, right? And what happens? Well, you win $50, but you don't really win $50, you really win $40. You're probably thinking, well, why? Well, because you gave them $10 to start. So they're giving you back your 10, so you really only made $40. What's the probability of this happening? Well, when you roll a die, the probability of rolling a 6 is always 1 out of 6. Well, what's the next best situation? Next best situation, you do not roll a 6, then you roll a 6. In that case, you paid them $10. They give you your $10 back. How much did you actually make? Nothing. What's the probability here? Well, we got to do some thinking. The probability of not getting a 6 is 5 out of 6. So we got 5 out of 6, then means times, and a 6 is 1 out of 6. So 5 out of 6 times 1 out of 6, multiply the tops, you get 5. Multiply the bottoms, you get 36. What's the worst situation? Well, the worst situation is you get no 6s, and then you get no 6s again. And if that's the case, unfortunately, they keep your money, so you're down $10. Well, what's the chances of that happening? Well, no 6 would be 5 out of 6. Another no 6 would be another 5 out of 6. 5 times 5 is 25, and 6 times 6 is 36. So if you remember, this is where we can't go any further in the table yet. We have to now look, and this question says, find the expected value. Great, we're going to do that. The expected value, which by the way, is another name for the mean, or mu in this case, is found by multiplying and then adding. So 40 times 1/6 plus 0 times 5 out of 36 plus negative 10 times 25 out of 36. And if you remember, we did all that in the calculator one time. There is no need to do them individually. You get a better answer when you only round one time. And since this is money, 2 decimals, and I'm getting negative 0.28. So that means that you're losing money. But that also means that we can finish our table. So this column that is now needing to be filled in, we take each x value and we subtract our answer we just got. So 40, take away negative 0.28, ends up being 40.28. Because remember, subtracting a negative changes it to a positive. 0 minus negative 28 gives us positive 0.28. And negative 10 minus negative 0.28 gives us negative 9.72. And so we need to square these. Remember, we don't actually type it in. We're just getting rid of the negatives. So 40.28 squared and 0.28 squared and 9.72 squared. And then all we're going to do is take each one of those numbers and multiply it by its probability. 40.28 squared times 1/6 and 0.28 squared times 5 out of 36 and 9.72 squared times 25 out of 36. And so we're going to come back down here because the other thing we had to find was the standard deviation. At this point, you add up those three numbers in the calculator. And if you remember, when you add those up, those are technically your variance. So when we add all of those up, we get 336.03 for our variance. But the only reason we bother to learn variance is because we need standard deviation. So the standard deviation, if we square root the variance, comes out to be, and again it's money, 18.33. So we found this information because this information represents the population. So mu is negative 0.28 and sigma is the 18.33. So now we're going to build on this and we're going to answer some sample questions. So you play this game 5 times in a row. Find the expected value and the standard deviation of your average winnings. Well, to find the expected value, we simply take, it happened 5 times in a row, so we take 5 and multiply it to our mean, which is negative 0.28, and we end up with negative $1.40. So if you play 5 times in a row, you're going to lose $1.40. Now, in order to find the standard deviation, we first have to find the variance. So we also have 5 of those variances. So 5 of the 336 03s gives us 1,680.15. So we square root that answer to find our standard deviation. And if you round appropriately, I get 40.99. So we now have our mean and our standard deviation if we did it 5 times in a row. But that's just us. So now we're going to look at the concept of a sample. 100 people now play this game. Bam. There's our sample size. What's the probability that the person running the game makes a profit? So we'll come back to that. So we now have a sample. This is where we need to calculate a sample mean and a sample standard deviation. Nice thing is, the sample mean is the same mean as the original problem, which is negative 0.28. The standard deviation for the sample is the population divided by the square root of n. So the population was originally 18.33, that's what we got from our table, divided by the square root of 100, and I end up with, it's actually a nice number, 1.833. Did you guys get that number as well? So we need to discuss this. What does it mean by the person running the game makes a profit? because this problem was all about you making money. Well, if the person running the game needs to make a profit, that means that you need to lose. So that means that your winnings has to be less than 0. There's your key number. This is your X. This tells you how to shade. So my z-score is going to be found by taking my x value of 0 minus my mean, which is negative 0.28, divided by my standard deviation I just found of 1.833. Be careful with the double negative. Remember, technically changes to a positive. And if you calculate that and round appropriately, I get 0.15. And so our graph with 0 in the middle and 0.15 right here, remember, you need to lose. You need to make less than 0. So you are shading to the left. Go to your blue sheet, z-score sheet. Look up 0.15, and I get 0.5596. So the chances of the person running the game making money is better than 50%. And so that's the end of our problem. And that's the end of chapter 18.